stops now. I was doing something right there when suddenly a Dalek walks into my classroom.
So there's this hunter, and he wants to shoot a monkey for some reason. Welcome back. This week we're going to have a look at measuring speed in a little bit more detail. Specifically, we're going to look at more practical situations in the lab and start to consider the role of prefixes in our calculations. The first example I'd like to share with you is in the context of running a marathon race. Marathons get their name from an ancient Greek sort of myth or story related to a battle that took place with the Persian Empire at the time, and one of the soldiers, after the Greek side won, had to run from the town of Marathon all the way to Athens to let the other people know that they had been successful. And he basically fought the battle that day, and then he ran the full 25 miles all the way to Athens, told them the news, and basically collapsed from exhaustion and died on the spot. These days, marathons are still used all around the world as a demonstration of truly impressive endurance. Most people who attempt them are aiming just to finish. So it's about 26 miles or 42-ish kilometers, a very big distance, and it takes quite some time. They shut down the streets in most major cities for it. It's quite a big spectacle. But in 2018, this guy here, I won't try and say his name, he set a new world record. He had a time of 2 hours, 1 minute and 30 seconds. That's really, really, really good. So what we want to do today is look at working out his average speed. The simplest units we could work in is probably miles per hour. So 26 miles divided by 2 hours means his average speed must have been 13 miles every hour. That's really quite impressive. But if we want to work in the more conventional kilometers, all around the world people measure distances in kilometers. We're kind of a slightly strange exception, and the kilo in kilometers is a standard prefix that we use all across science. So it's quite a good idea to get some practice using it. So our distance would be 42.2 kilometers, our time's 2 hours, and just like before, we can start our calculation with the equation, substitute in the numbers, carry out the sum in our calculator, and remember the units we get out for the speed are whatever units we put in for the distance divided by time. So kilometers divided by hours. If we want to do the same sum but end up with an answer that's going to be in meters per second, that's the standard units for speed in science, then we need to get rid of this kilometer and we need to get rid of the hours. We need to convert the units. Some people attempt to do this at the end of the sum. They take their final result and they try and convert that, and usually that ends quite badly. There's just a few too many steps and it's not a very good idea. Instead, what I recommend you do is before your calculation, you make a copy of the numbers and you do a separate sort of pre-flight check to deal with this. In the case of distance, the conversion factor we need is that a kilometer is 1,000 meters. This is actually true for kilo anything. A kilogram is 1,000 grams, a kilovolt is 1,000 volts, and a kilohertz is 1,000 hertz. It's sort of true for everything. Kilo means 1,000 of them. So a scientist would read this as 42.2 kilometers or 42.2 thousand meters. That's what kilo means, and it's one of the things you have to remember. Once we've got the two numbers, 42.2 times 1,000 is just 42,200. And again, calculators are your friend, make use of them, even if it seems like it's quite a straightforward sum. If we were to use these numbers, we'd have a unit in meters and it'd be divided by something in hours, and we'd end up with a sum that comes out as meters per hour, which is quite a strange unit. We should never really use that. So what we're going to do is now address the hour issue. People sometimes struggle, but it's quite surprising to me because I think everyone knows that there are 60 minutes in an hour, and everyone knows that there are 60 seconds in 1 minute. So if you want to know how many seconds there are in 1 hour, in other words, what can I swap hours for, 1 hour is the same as 60 minutes times 60 seconds, and that's what we end up with here. Doing this sum, we end up with 2 times 60 times 60, that's 7,200 seconds. That's roughly how long this guy was running for. If you put both of these new numbers into our equation, we get a new result, 5.86 meters every second. That sort of, it fairly fast sprinting pace. Most cyclists, for example, travel at around 7 meters per second. So it's really quite impressive. As I said before, this is about 13 miles an hour, which, as I say, most people, when they're sprinting at sport day, that sort of thing, or good runners, can sprint at this speed. Our record holder was so impressive because he did that speed for 2 hours straight. This little clip here, and so there's a longer video link here. I'll put a little link you can click on up in the corner here. But this is from Runner's World, and it shows a sneak peek of something that they're showing. They built a big treadmill and they set it to roll at the same speed as our marathon runner. They then took it to a big old conference and challenged random people to give it a go, trying to keep up that pace. Most people could manage it, but usually only for a very short amount of time. I find it really quite impressive that the best I could possibly sprint at for even a very short period of time, there's someone out there that can do it for 2 hours straight. That is thousands of times more advanced than I am. That is truly spectacular. As impressive as our runner is, it's actually quite easy to measure his speed. All you need to do is mark out a certain distance on the ground and time with a stopwatch how long it takes him to travel that 100 meters or so. That's quite achievable for most people, and you would get reasonably accurate results. If, however, you want to measure things that go faster, it can be a bit trickier. If you're trying to measure, say, a cyclist or a car on the road, well, you could probably do okay. If you try and measure, say, a helicopter or a fighter jet, it's really hard. And if you want to measure something that's really, really fast, like, say, the speed of sound traveling through the air, well, you're going to hit a pretty big problem. Sound travels at roughly 340-ish meters every second. That means in 5 seconds it'll travel a full mile, or it'll travel 300 odd meters in 1 second. So if you're going to try and measure that, you either have to have quite a big distance, in which case how do you see when they get to both ends of it, or you have to measure a very, very small time. And if you're relying on a human to do that, you're going to hit a basic limit. It takes an average person about 1/10 of a second just to push a button when they see something. So the smallest time you can measure is roughly 1/10 of a second or a bit bigger. If you have little distances like this one here, the time it takes the sound to travel over that distance is far less than this 1/10 of a second. Therefore, you end up with nonsense results, and it's basically just measuring your own reaction time. To allow us to do this in the lab, what we use is an electronic timer instead. This box here is called a TSA. It stands for time, speed, and acceleration, because that's what we tend to use them to measure. But today it's just a timer. It's a little computer chip that's very, very good at counting, and it's very flexible for what we use. If you continue to study physics, you'll use these year after year and gradually develop your understanding of a whole range of different topics. In this particular case, it's a demo. We have a pair of microphones spaced a certain distance apart, and we're going to make a loud sound, and the sound waves will travel along, hit this first microphone, which will send a signal to start the timer. Then the sound will keep going, reach the second one, and that will send a signal to the timer again to stop counting. These timing devices are able to measure hundredths of milliseconds. So that's 1% of 1,000th of a second. They're very, 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 very good. When we measure the distance along here in millimeters, that's sort of 1,000th of a meter. So that's also pretty good, but it's not quite as good as our time measurement. There is an alternative setup here. You can have a look at Mr. Murray's physics channel. He shows you how he used this piece of equipment to measure it with a computer. These microphones are a slightly different model, but it's the same idea. And this Alba interface is another common piece of physics equipment, and it allows these microphone signals to talk to a computer so you can plot it on the screen. I'll put another link up here for you to go visit him. Now, for a real example, this photograph is slightly misleading. They have put these microphones quite close together to get them in the shot, but in practice it's actually best to spread them out as far as possible. And if you have a bit of space, you can normally manage to make them about 2 meters apart and still have enough cable to plug them into this box. But for our example, I'm going to presume that they were spaced about 1 meter apart. But there's a subtle teaching point here. If I say something is a meter apart, or 100 centimeters apart, or 1000 millimeters apart, on the face of it, people say that that is the same number. It's the same size. And of course they're right. There are 1000 millimeters in 1 meter. But there is a subtle point here. If I tell you it's a meter, I sort of suggest that my measurement's quite rough. When I say 1 meter, what people hear is 1 meter-ish. Whereas if I say 100 centimeters, what people tend to believe is I'm saying that, maybe it's 100, maybe it's 101, but it's pretty close to 100 centimeters. And if I say 1000 millimeters, well, I'm implying that I've measured it to the nearest millimeter, so I'm quite sure that it's really, really close to that. But the thing is, I don't really like these prefixes. They make my sums more difficult, so I'd rather avoid them. So what I want to do is have a method that allows me to talk about the distance in meters, but still allows me to specify that I'm not talking about a meter-ish, I'm talking about 1 meter measured to the nearest millimeter. And the system physicists use for that is to carefully choose the decimal places. So instead of writing just 1 meter like we did here, I'm going to write 1.000 meters. This is the physics way of saying that I have checked and I've actually measured all these numbers. In a mathematical context, 1 and 1.0 and 1.00 and 1.000, they're all the same. But in physics, we consider them to be slightly different numbers. It's not that they have a different value, it's that we're claiming to be a bit more precise. When I write these numbers in, I'm suggesting that my number is quite well known. It's a careful measurement, whereas this one over here is a very rough measurement. This becomes relevant when you have to round your final answer, which we'll see in different examples. Now, when I do my experiment, when I set it all up, there's a bit of a problem. You see, I've got to push these buttons to prime the microphone, and then I've got to turn this thing on, and then hopefully everyone's completely quiet, and I get my result. Because if anyone coughs or nudges the table, these microphones are quite sensitive, and you can end up with rogue results, strange values that have nothing to do with the sound traveling through the air. So good scientific practice is not to just take one measurement, but to take several. Sometimes the measurement will be slightly too big, sometimes it might be slightly too small, and in general there'll be an average that is a good way to represent what's going on. You see, when I did my experiment, I tried to keep everything exactly the same for every repeat, but no one's ever perfect. Sometimes there might be a bit of a breeze in the room, it might be that it's slightly warmer, it could be that the electronics get a bit nudged, who knows, right? So there's these tiny little effects that I can't control, and that means my results randomly fluctuate just a tiny little bit. It turns out this problem is there every time everyone measures anything at all. It's just physicists tend to be a bit more honest about it and tend to spend a bit more time looking at that in detail. At the higher levels of science, all scientists do this, and it's kind of what makes science better than other areas of study. When scientists say they're sure about something, they're usually sure because they've checked how consistent their values are, whereas other people don't go to that level of difficulty. But one of the simplest justifications for doing this is if I try this measurement just once, and maybe someone's coughed, and I get a bad result. If I only have one number, I can't really figure out if it's good or not. I just have to either trust it or not. Whereas if I take several repeats, and they're all roughly the same, there's a very good chance that what I'm measuring is representative of what I'm trying to measure. It's unlikely that someone's going to cough at exactly the same time 4 or 5 runs in a row, unless someone's being deliberately difficult. You can also have a look at how much variation there is to get a sense of how well you've controlled all these random fluctuations, and in general, the overall average value of the data is the best estimate you can hope for. So to get that, I'm going to add up all these numbers and then divide by 3 to get the average. It turns out to be 2.94 milliseconds. So what I could do now is what I'm describing as the naive approach. The thing that you probably shouldn't do, but people often make mistakes and accidentally do. They say, right, I've got my distance, I've got my time, and the teacher's been talking about all this complicated practical work, and we gather up our data, and then I ask you all to calculate the value. And what people remember is speed equals distance over time, and they do that, they put the numbers in, and they get an answer. And then that's what they do, they just write it down. Usually, people remember that the units should be meters per second. That's what we like in physics. And that's what they do, they just write it in. They say, oh, meters per second. But there's a mistake. It's very, very unlikely that the speed of sound is 0.34 meters every second. That's about 30 centimeters a second. If that was the speed of sound, you really wouldn't be able to talk to anyone across the other side of the room. It would take several seconds for your voice to carry to the other side of the room, and that would just be really silly. So there must be a mistake. And it turns out the mistake's in the units. The sum's all fine. And the equation works for any unit, you just have to be consistent. So a technically correct but not very good answer would be to say my units for distance was meters, so this is so many meters every, and then the unit for time was milliseconds. So the correct units here are meters per millisecond. And that's quite a strange sounding unit, but it is technically correct. To do the sum and end up with a unit of meters per second, there are two different methods. The first one I think is easier to understand, but the second one is the one I recommend you go with. It's just a bit better for your long-term development. So, option 1. I could say my average time is this number, which is so many milliseconds. And my distance is currently in meters. If I change the unit of meters into millimeters, then I have millis in both my time and my distance, and when I do my sum, those two effects will basically cancel out. The conversion factor here is to recognize that milli means 1,000th, so there are 1,000 millimeters per meter, so that's 100 centimeters, and then times 10 because there's 10 millimeters per centimeter. So this number says 1,000 divided by 1,000, that makes 1 meter. That's the same as 1 meter, so that is consistent. And then I could put that into my equation, speed is distance over time, put the values in, and then my calculator will tell me that is 340 millimeters every millisecond. 340 thousandth of a meter in 1,000th of a second. And the factor of 1,000 cancels out, and we end up with 340 meters every second, which is what I expected. The best option, though, is to actually get rid of the prefixes altogether right at the start. So rather than manipulating the distance, we're going to manipulate the time unit. I'm going to say that milli is equal to 1,000th, 1 divided by 1,000, or just divide by 1,000. So that's basically what milli means, 2.94 thousandths of 1 second. That's how I read that. It's kind of the opposite of kilo. And again, this is one of the ones you need to remember. My calculator tells me that value is 0.00294 seconds, and now I'm ready to do my sum. Speed is distance over time, put the values in, and out pops the number straight away, 340 meters per second. It's in meters per second because I put 1 meter in for distance, and this many seconds in for time. So my units were meters and seconds, so meters per second comes out at the end. So measuring the speed of sound is a good demo, but the equipment that pupils typically use involves not that, but instead looking at cars moving along ramps for various reasons. We can have a look at basically the science of movement called kinematics or maybe mechanics, and that involves things like looking at how the force on an object affects its acceleration or how speed changes over time, as well as a whole range of other things. If you continue to do physics over the years, you will use this equipment multiple times for slightly different experiments, and it's a very, very good kit. There are a few different versions. For example, here we have our timing box shown in the previous slide, but there's also this slightly older version shown here. And we obviously have these nice metal ramps, or the slightly older, bulkier wooden ramps. They both do the job quite nicely. And last of all, we need to introduce a new piece of kit, this sort of light gate, or maybe light bridge. Before, we had a microphone that listened for the sound and told the timer when the sound wave arrived. Here we want something that's going to detect when the car is in a particular place. And how we do that is we set up a light source and a light detector. The light source is always on when it's plugged in, and then it shines the light onto the detector, and as long as there's nothing in between, nothing blocking it, it knows that the signal has been received and therefore nothing's in the way. That tells the timing box, don't do anything, nothing's going on. But as soon as our car comes along and interrupts the beam, so blocks this, what that does is it changes the signal that the sensor's getting. If the sensor suddenly doesn't get any light, and we know light's given out, it must be that something's in between there. That tells you your car, or whatever other object you're looking at, is in the particular position. That's typically when you start your timer, and then maybe you have a second one later on that tells you to stop the timer. A little side note on just the words for things. We sometimes call this a car, or it could be a cart, or it could be a buggy or something like that. And the bit of cardboard or plastic or sometimes metal that's on top is designed to basically go through the gate. We sometimes call that a card or a mask or a fin perhaps. There are a few different words for it, but it's all just a thing that goes through the gate. You can sometimes set it up so that the light beam is level with the actual car itself, but it tends to be a little bit trickier and we don't like doing that. The next idea to consider is there's actually some subtle differences in how we measure speed, or even what we mean by the word speed. In the case of our marathon runner, it's probably not really true that the speed was consistent throughout the whole journey, but it doesn't really matter if sometimes it's a bit faster and sometimes it's a bit slower. In the case of our speed of sound, well, chances are it was a single value all the way across the room in the lab. But if we talk about something like, say, this example, where we have a car that's traveling down a ramp, we're pretty certain that the car is going to get faster and faster and faster. Sometimes you might be interested in the overall average, but more often than not, what people are interested in is the particular speed at a particular point. Usually, in our context, the speed at the bottom here. And measuring the overall average doesn't really help. The idea is we distinguish this between average speed and speed at a particular instant, that we call the instantaneous speed. What we mean by that is how far are you traveling right this particular time. So if you say I'm going 50 miles an hour, you're not meaning really that you're going to travel you're not going to travel 50 miles in the next hour. You're sort of talking about a rate. You're really going to go so many meters in the next second, that kind of idea. But we can measure this in two different ways. The first method for measuring the average speed is kind of like how we did the sound. We have two inputs, two different light gates or light bridges, one near the start of the journey and one near the end. Our car is going to have its mask and it's going to go through both gates, and when it goes through the first gate, it'll block the signal, and that will cause the light gate to register that with the timer, and that starts the clock. When it reaches the second one, the signal is going to be used to stop the clock. A typical question you might get asked on this might look something like this here. A cart takes 4.53 seconds to travel between two light gates that are 160 centimeters apart. Calculate its average speed. Notice here they're deliberately giving you centimeters to make life slightly difficult, but that's okay, we can handle that. I should say that if you're doing this in class, the TSA boxes require you to tell them what you want them to do, and the setting for this is called the gap time. There's not really much you can learn from a video about this, other than you have to have the correct setting for the correct type of behavior. So in terms of our numbers, we have them here. It's always good to write them out separate, particularly if you have to deal with any pesky unit issues. And here, we could put centimeters into our sum like before, but we're in a good habit now where anytime we see a prefix, a milli, a kilo, a mega, a giga, that sort of thing, including centi, we just get rid of it straight away. Now you might say, well, I don't really know what centi is. Well, of course you do. If you think of meters, you know that a centimeter is 100th of a whole meter. So centi in this case just means 100th, and that's always true. This says 160 hundredths of a meter. And if we swap out the c in centi for divide by 100, we can then carry on as before. We've figured out that it's 1.60 meters is the same as 160 centimeters. A lot of people struggle to visualize what's going on here because they think centimeter is a whole thing, but it's not. The centi is a modifier. It's sort of telling you types of meters, pieces of meters. So again, 160 hundredths of meter is the correct way to read what this says. Once we have our time in seconds and our distance in meters, we can use the equation as before, and that's nice and easy, hopefully. At this point, I'd like to take a little bit of a side note to talk about how to round our final answer. You see, if I plug this into my calculator with slightly awkwardish numbers, I get a very, very long decimal. And many people feel that it's better to write down as many numbers as possible. What people kind of have learned in maths is this is the correct number, and if you round it, you're making your answer slightly worse. But that's not really true. If you remember what I said before, in physics, we consider the number of digits you're writing to have a physical significance. We interpret them to mean certain things. So if I write this as my final answer, how a physicist will read that is to say that I think I've measured it so carefully that I can talk about what this digit is. I'm not saying it's 0.37-ish, I'm saying it's exactly 0.372093.023-ish. So the ish is just on this digit here. And that's not really fair. That's a bit misleading if I say that. Because when I measured my distance, I measured it, well, 3 digits. When I measured my time, I measured 3 digits. And I should end up with the same out here. So the first 3 perhaps digits have been measured carefully. To be honest, it's not quite certain if we measured that one there, but I'll say we have. So when it comes time to round your final answer, you should round it to match what your data is. If you've got 3 numbers here and 3 numbers there, you should only have 3 numbers here. And zeros right at the start, they don't count. It's just the 3 numbers that actually mean something. So in this case, the correct thing to write is 0.372 meters per second. Now, if you were to have a little bit extra or maybe one less, we're going to be tolerant and we'll still give you the marks and things. But don't write loads and loads and loads of digits. In a similar way, you can also use things like the recurring notation or fractions, because those imply millions of digits. We don't like that. The second type is to look at the instantaneous speed. It could be near the start, the middle, or the end. In some experiments, we actually measure 2 instantaneous speeds. We have 2 light gates that each work separately with the timing box. But to measure one speed, you only need 1 light gate. And the setting we use is called time interval. That's basically saying, measure how long this mask blocks my light gate for. So we always need 2 time events or 2 signals to work the clock. The first thing turns the timer on, the second signal turns it off. In this case, both of them are going to come from this 1 light gate. As soon as it gets blocked, that's the first signal, the clock starts ticking, and then once it is no longer blocked, once the light reaches the sensor again, that's the signal to stop. And the TSA box is programmed to understand this. So obviously it's only going to take a very small amount of time for this mask to go straight through. You can see this one here is made out of metal. But we need to consider what distance it's going to cover in that time. And this is the bit I think most people struggle to understand. So I have this picture to try and help you. At the moment, this sort of video has been frozen in time a fraction of a second just before this mask is about to cut the light beam that's right here. So this is kind of the start. If you imagine the clock is going to start here. And then time will go on a little bit, and at some point later on, the light beam will come back. And I want you to think about where will the car be when that happens. Well, the answer is it's going to be in this position. So this is the shape of the mask, here's the location of the sensor, and you can hopefully see that from this time onwards, the light beam will no longer be blocked by the mask. You can see that I've actually tied this off to pose for these photographs. So if I ask you the question, how far has the car travelled in distance during this sort of time period, you can actually read it off the scale here if you want. But it's the same as the thickness of this mask. So it went from being at the start of this position to the same bit in the car being over here. That's equivalent to measuring this distance or this one, the distance from any point in the car to the same point in the car when the mask gets out of the gate. But it's easiest to measure the mask itself. So this is the kind of size we're talking about, and if you take a ruler, place it against the mask, and you can measure it fairly carefully. It tends to be that teachers, when they make these things, we tend to make them so that it's a whole number of centimeters. The reason for that is the magic timing box can also be programmed to know what this distance is, and in some experiments we have it work out the speed automatically for us. That's really quite handy. So a whole number of centimeters, or roughly so, is to be expected. In this case we have 4 centimeters. So for a worked example, what might this look like? Well, if we have our light gate here at the bottom, a car is going to come down through this ramp, and we're going to get a time readout here at 0.033 seconds, and we measure the thickness of the card, let's say 40 millimeters or 0.4, that's our 4 centimeters, and then we have to do our usual sum. Converting from 4 centimeters into meters means, again, the centi is divided by 100, so 4 divided by 100 is 0.040 meters. We then do speed as distance over time, put the numbers in, and out pops an answer. Here it's about 1.21 meters per second. Some people again might be tempted to have the recurring notation here. That's something you should never do in physics. We always insist upon a decimal final answer, because how much rounding you do shows people the quality of answer that you're claiming. Here I've rounded to 1.2 because we have 2 digits here, so 2 digits there. That's all the new theory this week. Can you have a go at the various homework questions as usual, and I'll see you next time.